going to guess that you came here to learn about similar figures. Well, you came to the right place. That's what we're going to talk about. Similar figures. Now, just in everyday conversation, you might say something similar that's not actually mathematically similar. Like, for example, you might say that this picture here is similar to this picture. They have some features the same. You can tell it came from the same picture. But are they mathematically similar? The answer is no. There's a lot of distortion that went on here. In fact, boy, I don't know. The first picture was pretty bad. That one's kind of creepy. Same with this one. It got real tall, but skinny, skinny, skinny. So that is not mathematically similar. What we're talking about with mathematically similar is something like this, where the original picture's just been reduced, but nothing else has changed other than the size. It's not been distorted in any way. And so with similar, like these two triangles, if triangle 1 is similar to triangle 2, then we say they're similar by using this symbol right here. That similar symbol. That little wavy, and basically it was stolen from the congruent sign. Congruent means equal in size and shape. We steal the little wavy part and we call it similar. So let me get rid of the wavy, of the equal part. Similar. All right, so basically similar means this. They are going to have the same shape. They'll be the same in shape, no distortion. But you're definitely going to have one large and one big. And so they are either an enlargement, depending on which way you start. You either get bigger or a reduction. You can reduce it down in size. But that has to happen proportionally, and that's what we're going to do. We're going to formalize this. When you have similar polygons and you're trying to show technical, mathematically similar, then you need two things to happen. Number one, you want to check if those polygons are similar by seeing if their corresponding angles are congruent. And then number two, do they have corresponding sides that are in proportion? And that's why we did proportions in this last video. Okay, so let's get a picture of this. With the magic of technology, I'm going to sketch myself a trapezoid. You're going to have to draw that the best you can. Then I'm going to take a copy of that trapezoid and I'm going to enlarge it. We'll make him bigger without changing anything else. All right, so we have these two trapezoids and they're similar. Let's name them according to the statement. So we've got trapezoid SIMA, just working my way around, and then, oh, look at this, similar, huh? Get it? Get it? Yeah. Okay, but it's in the same correspondence. So S was here. I'm going to start with L, matching it, and work my way around in the same way. L-U-R-E. Okay, so I've got sima, similar to lure. And what does that mean? Well, number one, it means the corresponding angles are congruent. That means S, which corresponds to L, those are congruent angles. Also, around here, I has to be congruent to U. Angle M has to be congruent to angle R. You get where I'm going with this. Angle A is going to have to be congruent to angle E. And so we know how to write that in symbols. We're just going to list that out. Angle S is congruent to angle L in the large one. Angle I, that one was congruent to angle U. Angle M congruent to angle R. And angle A was congruent to angle E. Nothing really too tough about that. Let's go to number two. Now that we've shown the angles are congruent, we have to show the corresponding sides are proportional. So what does that mean? It means we're going to take the sides. Let's start with this one here at the top, SI, and its corresponding side is LU. I'm going to show that that's in a proportion with the other side. So SI divided by LU, making a ratio out of it, is equal to, when I do it to the other sides, IM, for example, in blue here. That is corresponding to UR. It needs to be in the same ratio. So IM compared to UR, and that needs to work for all the sides. So this is going to take some working around. We're going to go AM compared to the bigger one of ER. And then wrap it up with the last pair of sides, which are SA, and that's going to be corresponding to LE. And all of these need to be equal ratios. So this whole proportion needs to say they're all the same. They're proportional. So that's the test. You got to check the angles, and you got to check the sides to be in proportion. If you got that, you've got similar polygons. Let's work this example. So we're going to test, are these figures similar? If they are, we'll write our statement and our scale factor. So number one, we're going to check the angles. Let's see how our markings look. We've got an angle L, looks like it's been marked as congruent to angle P. Notice they have turned this, looks like they may have flipped it around too. So we've got angle L, and we know it's congruent to angle P, that's just given. We also have angle M at right angle, that matches angle N. And then what about our last angle that they told us nothing about? Are those going to have to match? Think about that. In fact, let's put some numbers in here because I think they're matching. Let me just prove it to you. Let's say that this angle L here was a 20-degree angle, and I'm making it up. It could be anything. But it would have to match angle P because it's tick marked to match. So you have 20 and 90. What's that last angle going to be? Well, we'll add these up. 20 and 90 makes 110. Subtract from 180. This will have to be 70. So are you going to get a different answer when you figure out angle S here? You still have 20 and 90, subtract from 180, you're going to get 70 again. So sure, if two of the angles in the triangles match, the third angle has to match. We've got enough to say that these are all congruent angles. So angle J is our last one. It's congruent to angle S. All right, so the angles check out. They are definitely congruent. Now we need to check the sides to see if they're in proportion. I'm going to start here with LJ, which is my longest side, and match it up to the longest side here. That's PS. So that's 75, and that's going to go with the 30. Set that equal to, let's see, let's do this in green. So how about 60, this middle side down at the bottom? Which side's going to come next here? The middle side. That's going to be 24. So 60 compared to 24. And then finally our 45 would match up with our 18 as a corresponding side. So you just have to match them up. The important thing, notice I'm doing the big one compared to the little one. And you can switch that around if you want to. The only thing you got to make sure of is that you're consistent, that you do it always the same way through the whole problem. Okay, well, how do I know if these are in proportion? These are all just a bunch of random numbers. What I'm going to do is divide it out to check. So let me grab my calculator. So let's take 75 divided by 30. And that's coming out to 2.5. The others have to match. So does 60 divided by 24 give me the same result? Sure enough. All right, don't stop till you're done with all three of them. So 45 divided by 18, 2.5 all the way down. So these are definitely in proportion. Those are equal all the way. Check that. Now we're going to write our scale factor. That 2.5 that we were getting, that's the scale factor. That means that my big one is 2.5 times the size of my little one. If I take all the little ones, those little sides, and multiply by 2.5, I'm going to get all these big sides. Okay, finally our similarity statement. So how do we set this up? Just like when we did congruent triangles, you got to put the matches together. If I start with L, and let's go LMJ, then it's similar, there's the symbol, similar to what matchups? Well, L we had matched with P, so that one's first. M, that went with N, the right angles, and then finally we would have J matched up with S. So that same thing we did with congruent triangles back in Unit 4, same thing applies to similar triangles. There's our similarity statement, and there's our scale factor. Cool. Okay, let's look at a couple of examples. I'm going to hide this one here. Let's start with this one. So these figures are similar. We can trust then that they have congruent angles and proportional sides. Let's find the value of x. So x looks like it's the short side. This kind of looks like it's a parallelogram, but that shorter side is going to match up to the short side of this one. Let's just put x over 3. And then as our second pair, it's pretty easy to see, we're going to go 12 inches compared to 5. So 12 over 5. There's our ratios, set equal to each other. And just to show you, it doesn't matter the order you do these in. I'm going to also show you that you could take the 3 over the x, so go short to big. As long as you're consistent and you put the same short to big on the other pair, you should get the same answer. All right, we've practiced this, so we're going to cross multiply. Let's take the x times the 5, that's 5x, and that's going to set equal to 3 times 12, or 36. Divide both of those by 5. And then, so x is going to be 36 over 5, which is a good answer to me, but you guys probably like to turn that into a decimal. So if you just divide that out, I believe it's 7.2. You'll have to correct me if I'm wrong. So x is 7.2, and this would be in inches just like the other units were. Do you get the same thing with this one? Well, sure. Look at it. You cross multiply, you're still going to have x times 5, and you're still going to get 3 times 12. So the consistency is the important thing. This will still give you the same 7.2. Hopefully that works for you. Let's take a look at this table example. So we have a child's desk, which is a scale replica, and I'm going to circle that. That's important to know. It's a scale replica of the adult-sized desk. That means everything stayed in proportion. That right there means they're similar. So if it's x long inches, this is this child's desk, x inches long here, what does that match up to? That'll be our 54 inches to match up. So x is to 54. Set that equal to 24 inches on the width, matched with 36 inches on the actual width. So 24 first, 36 next. So notice I did child, compared that to adult, and I stayed consistent on both. All right, let's knock it out. So we've got 36 times x in the cross multiply. Ooh, that's a 6. And we've got 54 times 24. I don't know what that is. 54 times 24. My calculator tells me it's 1296. Dividing by 36, and 1296 divided by 36 is 36. So the child's desk is going to be 36 inches on this dimension here. Sweet. All right, so that's similar figures. That's pretty much what this unit is. We're going to get a little deeper into it, maybe a little tougher as we go, but that's it in a nutshell. Try these questions a shot.